Hello and welcome to another video on this channel. I have done quite a lot of videos in this series of inorganic chemistry, general chemistry slash, but I feel like I haven't talked much about this topic. So that's why we have this video today. And in this episode 10, I will talk about electronegativity, and ionization energy. So it's quite an important concept. So I need to really clarify for you so you can understand further topics like easier, and also you can understand like previous topics clearer as well. Now, first of all, what is electronegativity? So electron negativity is defined as the ability of an atom to attract electrons. It doesn't matter where, but it just attracts electron to it. So the ability of an atom to attract electron to it, okay? So it can be like the electrons from other atoms in the same molecules. It could be electron from different molecules, but anyway, it's just attracting electrons from the environment to that atom. And that ability is called electronegativity. And the next one is ionization energy. So by definition, what is ionization energy? It's the energy required to remove the last electrons from the last electron from the atoms. So basically, for example, say let's just look at say lithium, for example, lithium 7,3. So you would put this 1s1, the first electrons, the second electrons there, and this is the last electron you put into the electron configuration, right? This is the last electrons. So the first ionization energy is the energy required to remove that last electrons from the neutral atom, okay? From the neutral atoms. I'm not talking about like ions, okay? From the neutral atom. So basically, let's just say I want to turn lithium into lithium plus and then 1 electrons. So the energy required to do that, to remove 1 electron from the lithium, so it becomes from a neutral atom to an ion, or in this case a cation, that energy is called ionization energy, okay? And so on, of course, to a lot of other atoms, a lot of other elements, the same thing applies. So if you want to remove the last electron you put into the electron configuration, that energy required, it's called ionization energy. So we have something called first ionization energy, second ionization energy, third ionization energy, fourth and fifth, and so on. So what do they mean by this kind of order? So let's say first ionization energy. Okay, let me just make it easy like this. Now let's look at lithium, for example. So if I want to turn lithium into lithium plus and then 1 electrons, that's the first step. That's the first electron I get. I just pull it out, and the energy required is called first ionization energy. However, if I want to remove even further, so it becomes lithium 2 plus, and then I want to remove 1 more electron from that, the energy required, it's called the second ionization energy. And if I want to even remove further, I can do that, of course. But of course, I would need a lot more energy because I have to go through like 3 different processes, right? So that one requires something called third ionization energy, and so on, of course. As long as there are, how can I say, more, as long as there are still electrons to be squeezed out of the atom, then you will still have like other kind of ionization energy. Now, so that is first, second, third, and so on ionization energy. So, well, we are talking about like simple atoms, simple elements, metal and non-metals from, let's say, the second and the third group in this video. So I'll go back to ionization energy later, but now let's deal with an easier concept of electron negativity. It's easier doesn't mean it's less important, okay? It's still important. Now, electron negativity, the ability of an atom to attract electron into it. Now, first of all, let's just review what are metals and non-metals. So you know that metals are the one that in group 1A, 2A, 3A, something like that. They are all the way to the left of the periodic table. And non-metals are the one on the right, like group 5A, 6A, 7A, something like that, yes. And metals, they have this kind of property, you can see here, they conduct electricity well, because you know metal, basically this pen is made out of aluminium, and metal, they tend to form a kind of structure called a lattice. So it's a network. It's a network of atom, and in that network, let me just draw it. For example, I could just draw it like this. So it's a piece of aluminium, let's say a piece or a network or a sheet of aluminium can be composed of so many aluminium metal elements, okay? So many aluminium atoms. And there are electrons. There are electrons flowing inside. There are electrons flowing inside of this kind of structure. This kind of structure is called lattice. It's a network made out of metal and electrons of it. Now, so the electrons in that lattice, they don't stay in one place, but they move. That movement is called delocalization. De means remove. Localize means they stay in one place. So delocalization is the process that they move out of place. They move around that network. They move around its lattice. And due to this delocalization of electrons in the lattice, it makes the metal conduct electricity. So it gives the metal the ability to conduct electricity. Because you know electricity is just a flow of electrons, right? So if the lattice is like this, electrons move around freely, it means the piece of metal can conduct electricity well. Okay. Now, next one, metal, they have low electronegativity. As I told you in a previous episode, they have low first ionization energy. So it means it's very easy to remove the last electron away from it. And it's malleable. Malleable means like you can just bend metal very easily into any shape you want. Alright, and then non-metal, they do not conduct electricity well because they don't have this kind of lattice structure and they don't have the localization of electrons. And non-metals, they're all the way to the right. So in my previous episode, I said that non-metals often have higher electronegativity. And now, they have higher first ionization energy as well compared to metals. Now, let's go into details. What is electronegativity? Again, it's the ability of an atom, a neutral atom, to attract electron to it. Now, let's look at lithium, for example. It's in 1A group, it's a first metal. Look at its electron configuration. So, these last electrons is put into this empty S subshell. So, what do you think? Is it easy to remove these lonely electrons? Yes, it is. If you look at this table, this kind of chart, you can see that lithium have relatively low first ionization energy. So it's quite easy to remove this electron because it's lonely. It's alone in this S subshell. Now, as you move, to beryllium, the first ionization energy increases because now these electrons are the one who needs to be removed, and since this S subshell is full already, it's more difficult to remove this electron, because this S subshell is full already. It doesn't want to give up that much. So that's why shielding effect is something we see in the textbook. It shield each other, protect each other. So that's why this electron is more difficult to be removed. So that's why increase in ionization energy, first one. Now, as you move to boron, now this is the electron that needs to be removed, and it's in the empty or relatively empty P subshell. So it's empty, it's lonely, so it's relatively easier to remove compared to this case. So that's why the first ionization energy of boron dropped down a little bit, you can see. Now, move on to carbon and nitrogen. For carbon, this is the electron you need to remove, and they are here, but now, in this case, they are shielded by these next electrons. So shielding effect, they protect each other. So that's why carbon have higher first ionization energy compared to boron. And you can guess, nitrogen is also because you have two things guarding it, shielding it. Now, okay, when you move to oxygen, why it drops down like this? Because now these electrons are the one that needs to be removed. Well, compared to other two cases, this electron seems rather easier to be removed compared to this nitrogen case, because this electrons doesn't seem to be shielded very well by these three. Up, but this one is down. So it's not really easily being shielded by the other electrons. So that's why this one dropped down. Now, for the fluorine, well, because you have these down electrons shielding these down electrons here, so shielding effect applies, it protects this one. So it's harder to remove this electron compared to the oxygen case, right? And of course, neon, don't even mention it. Neon actually achieved the 8 octet, full octet already. So it doesn't want to give up. It doesn't want to give up any electrons. It just full already. It doesn't want to give up. So that's why for noble gas, neon or any kind of noble gas, it is incredibly difficult to make into an ion or to remove one electron from it. So that's why very high first ionization energy for the noble gases. Well, there's also another way to explain the fluorine and oxygen as well. For the oxygen, this atom want to receive 2 more electrons to fill in this half-empty subshell. But they don't want to give up this one that much, right? For the fluorine, it wants to receive 1 more electron in here, very bad. It doesn't want to give up this one, but it just wants to receive. And for neon, it doesn't want to give up anything. Alright, so when you go from neon to sodium, why a huge drop in first ionization energy? Sorry, why the huge drop in first ionization energy? Because now sodium has a very lonely 3s1 half-filled subshell, and it's very easy to remove these electrons, so it goes back into this kind of configuration of a noble gas neon. It's more stable like this compared to this one, right? So that's why it's very easy for the sodium to give up these electrons. Very easy to give up. So that's why first ionization energy of sodium is even lower than lithium. But the question asked is, now you can see the trends. It's very similar for the group for the period 3 atoms or elements. You can see the similar trends, you know, and I can also explain similarly like that. But the question is, why the ionization energy, the first ionization energy of sodium, it's lower than lithium? Who can answer that? Well, simple. Think about this. For lithium, 2s1, this electron is very near to the nucleus, isn't it? Compared to this electron, which is further apart from the nucleus of the sodium. Nucleus are basically positively charged, and electrons are negatively charged, right? So they attract each other. However, if they are further apart, the interaction are weaker. So it means you have stronger interaction between this electron and the nucleus of lithium compared to the interaction between these electrons and the nucleus of sodium. So it means what? Sodium are basically easier to give up these electrons compared to this lithium electron, right? That is the reason why you need less energy to remove the first electron from the sodium compared to the first electron of lithium. I hope that was easy to understand. Yep, I think. And you can say the same for all the rest of them. Basically, further apart from the nucleus, you know, so they are less well guarded, they are less guarded, so it's easier to lose them. And hence, easier to lose them, you have lower first ionization energy. Now, how about electronegativity? Why, when you go from the left to the right of the periodic table, it increases? Who can explain that? Well, as you know in my previous video, as you move from the left to the right, the atomic radius just keep basically decreasing, isn't it? And the atom getting smaller becomes smaller and smaller. So the distance between the last electrons and the nucleus decreases as you go from the left to the right. So of course, what does it mean? Well, they're more protected when you go from the left to the right. But that is not the reason why the electronegativity increases when you go from left to the right. What is the reason here? Okay, look at the case of fluoride, for example. Its electronegativity is 4.0, which is the highest in the whole periodic table. in the whole periodic table. Why? It only wants to receive electrons to fulfill this this last place, right? It's like eager to receive the electrons so much. So that's why it has a very high electronegativity. But look at, say, lithium, for example. It want to give up these electrons. It's very easy to give up these electrons. So that's why it's the opposite of fluorine. And that's why it explains that lithium, all the way to the left, has very low electronegativity. So, in short, metals easy to give up electrons. So that's why it has low electronegativity. Non-metals, very easy to accept electrons. So that's why it has high electronegativity. Alright. And also, I think I already explained like low ionization energy and higher ionization energy. So I think that was quite enough for this video. I hope you find it helpful. Please like, share this video with your friends, subscribe to my YouTube channel, and press on the bell button next to the subscribe button so you can get notified about my new uploads. You can also follow my Facebook, but please don't add me on Facebook as friends, okay? Thank you, bye!